Okay, let's unpack this. Have you ever heard that saying, do the simplest thing that could possibly work? It sounds so straightforward, right?
Uh,
Almost obvious.
yeah, on the surface.
But what if I told you this phrase, often shortened to DTSTTCPW, is actually one of the most, well, fiercely debated and nuanced principles in software engineering?
It really is. You see discussions online with hundreds of comments, engineers really grappling with what it means.
Exactly. It shows just how deep this goes.
And the thing is, DTSTTCPW isn't really a rule you use in isolation. It's part of this whole ecosystem, this philosophy about handling complexity, being efficient, and keeping software healthy long term.
Right. So today, we're diving deep into the sources we've looked at to really understand this principle.
And its close relatives like, you aren't going to need it, YAGNI, and keep it simple, stupid, or KISS.
And we have to talk about its main sort of conceptual opponent, premature optimization.
Definitely. Our mission here is to show why applying the simplest thing isn't just a beginner move, it's actually a sign of real expertise.
And how its meaning gets forged in the context of, specific problems, team cultures, even economic realities.
So what does this actually mean for you and how you approach problems? Let's dig in.
So we're fundamentally talking about managing complexity, right? In a field that just seems to churn it out endlessly.
That's the core challenge.
And your sources make it clear this isn't just one idea. It's like a whole constellation of related principles. Let's start with DTST-TCPW itself. It originates from Extreme Programming, XP.
Correct. And its main purpose, really, is to stop engineers from over-engineering, from building stuff for a future that might just never happen. Speculative design, they call it.
Okay, but here's where it gets really interesting, I think. You mentioned it's not used alone.
Exactly. That's critical. DTSTTCPW relies on this robust safety net. We're talking continuous refactoring, comprehensive automated tests, unit tests especially, and continuous integration.
Without that net.
Well, without that support system, just blindly doing the simplest thing can actually lead you down a path to messy code, maybe disorganized systems, and eventually huge technical debt.
Right, it needs the discipline around it.
Precisely. And if we connect this to the bigger picture, that safety net idea brings us right to you aren't gonna need it. That's kind of the philosophical engine behind DTSTTCPW.
Coined by Ron Jeffries, another XP founder.
That's the one. And the mandate is pretty clear. Always implement things when you actually need them, never when you just foresee that you might need them.
That directly tackles that urge we all sometimes feel, right? To build for every possible future scenario.
It does, and it's a hard lesson. Even very experienced developers like John Carmack noted struggle with this. It's tempting to future-proof everything.
And there's a really strong economic reason behind YAGNI too, isn't there? It's not just about code purity.
Absolutely. That's a key driver. You have to ask, what are the actual costs of building something you don't end up needing? Well, the sources break it down into three main costs. First, there's the obvious cost of building the time, the resources you spend right now.
Makes sense.
Second, there's the cost of carry. Unneeded code isn't free. It adds complexity, makes the system harder to grasp, harder to maintain. It's like carrying extra weight in your backpack you don't need. It just slows you down.
I like that analogy. And the third?
The cost of delay. This is the opportunity cost, that time you spent building the unnecessary thing. You could have spent it on features that deliver real value now.
Ah, okay. So YAGNI helps you minimize all that waste by basically putting off decisions until you absolutely have to make them.
Exactly, until the last responsible moment. It fits perfectly with agile thinking respond to change rather than trying to predict everything up front. It's about optimizing the decision-making process itself.
So YAGNI tells you what not to build too early. But then there's KISS, keep it simple, stupid.
Yeah.
Which seems more about how you build it when you do build it.
That's a good way to put it.
And this one has a pretty cool origin story, right? U.S. Navy, Lockheed Skunk Works, 1960s.
Yeah, fascinating stuff. The lead engineer, Kelly Johnson, supposedly challenged his team designing jet aircraft. The core idea was, these planes need to be fixable by an average mechanic out in a combat zone with just basic tools.
So the stupid part wasn't insulting the designers.
No, not at all. It was about the conditions of repair. The system had to be fundamentally simple enough for someone without the designer's deep, immediate knowledge to maintain it under pressure.
That translates so well to software, doesn't it?
Powerfully. KISS in software means prioritizing clarity, readability, straightforwardness over maybe clever, tricky solutions.
Yeah, code that looks smart but nobody else can understand 6 months later.
Exactly that. Simple code is just easier for new people to onboard, it's easier to debug, and frankly, it usually has fewer places for bugs to hide, less surface area,
So it reduces the mental load, the cognitive overhead.
which directly lowers the total cost of ownership. Better maintainability, less effort for future changes. It's actually a strategy for future-proofing, but by reducing friction, not by adding speculative features.
Okay, so we have these principles pushing for simplicity. Now let's talk about the counterforce, premature optimization.
Ah, yes, the root of all evil.
We always hear that quote from Donald Knuth, right? Premature optimization is the root of all evil.
We do, but often out of context. The sources highlight the full quote, and the nuance is absolutely crucial.
What's the full version again?
We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%.
Ah, okay. That changes things quite a bit.
Hugely. Knuth wasn't saying never optimize. He was railing against optimizing before you know where the real bottlenecks are, before you've measured.
Right, because you might spend ages optimizing code that barely runs.
Precisely. Data consistently shows that performance issues are usually concentrated. Often something like, 10% of the code accounts for 90% of the execution time
So optimizing the other 90%.
is often a complete waste of effort. It makes the code harder to read, harder to debug, and you get almost no real-world speed up.
So the right approach is,
First, make it work. Write clear, correct code. Then make it right. Refactor for clarity and good structure. Then, and only then, if needed, use profiling tools to find that critical 3% and make it fast.
and this is different from just making good design choices up front, like picking the right data structure.
Absolutely different. Choosing appropriate high-level architecture or fundamental data structures isn't premature optimization. That's just sound design. It's about knowing the difference.
Okay, so DTSTTCPW, YAGNI, KISS, and this careful approach to optimization, they all weave
When
together.
they form an interconnected system, yeah.
And it sounds like they're not just coding preferences, they're really strategic business decisions.
Yeah. That's the lens to view it through. It's about reducing waste, speeding up delivery of actual value. Over-engineering isn't just a technical mistake. It's often a poor use of resources, of capital.
That economic framework really clarifies the tension, doesn't it? The engineer's desire for a perhaps perfect system versus the business need for efficiency.
Mm-hmm. Perfect can be the enemy of good, especially if good enough now lets you learn and improve faster.
Okay, that all sounds great in theory, but as the sources really dig into, especially looking at community discussions, the real world gets messy.
Oh, absolutely. This is where the nuances, the contradictions, the crucial role of context, it all comes flooding in.
Yeah, so what are some of those complexities?
Well, one central theme is just the ambiguity of the word simple. What does it even mean?
Yeah, I don't...
The community often draws a distinction between simple and easy. Easy might just mean it's familiar or it takes less effort right now, but that easy path can sometimes lead to a really complex, tangled system down the road.
Like taking a shortcut that ends up in a swamp.
Kind of, yeah. Whereas simple really refers to the absence of complexity. Fewer moving parts, fewer interconnections, think clean lines, minimal dependencies.
There was that SMBC comic framework mentioned in the sources. Kind of humorous, but pointed.
Right. It suggested complexity comes from in order, the number of things interacting, then the complexity of their interaction, and finally the complexity of each individual thing.
So it prioritizes reducing the number of components and how tangled up they are.
That's one view. But then you have alternatives, like Rich Hickey, the creator of Clojure, argues you should prioritize making individual components simple, even if you have more of them, as long as they combine cleanly. Less internal complexity per piece.
Okay. So different ways to slice simple. How do you choose?
And how do you even measure it? That's the kicker. There's no single universal metric.
Like that example of a type explosion.
Exactly. That's a great example of where the first view can fail. You might have tons of slightly different data structures, maybe tightly coupled. Each one looks simple in isolation, but the sheer number and the way they interact creates massive overall complexity. It's like death by 1,000 paper cuts for maintainability.
Okay, so defining simple is tricky. What about the scalability boundary? What happens when the simplest thing that could possibly work just won't work because the scale is too big?
Yeah, this is a really powerful counterpoint. When you're talking systems that need serious performance, Massive scale.
Like handling thousands of concurrent users.
Right, like the C10K problem, handling 10,000 concurrent connections, or needing sophisticated connection pooling or circuit breakers for resilience in microservices.
In those cases, a truly naive, basic implementation.
It just flat out wouldn't possibly work. It would crash and burn. It wouldn't meet the fundamental requirements.
So the definition of work is key.
Absolutely critical. In those high-scale domains, the simplest thing that could possibly work is actually an inherently complex architecture. It has to be designed from the ground up to handle that load, that concurrency. The complexity isn't arbitrary. It's essential complexity required by the problem itself.
Okay, that makes sense. Then there's the abstraction dilemma mentioned in the sources. Using a library seems simple, right? Outsource the problem.
It often seems simple, yes, but it can lead to what are called leaky abstractions. You haven't eliminated the complexity, you've just hidden it behind an interface that might not perfectly match your needs or might have its own subtle issues.
And debugging that can be a nightmare.
It really can. Trying to figure out why a system built on layers of these black box abstractions isn't behaving as expected. It can be incredibly difficult and time-consuming.
So it's a trade-off.
It's always a trade-off. An external library is simple if it's a perfect fit and bug-free, but if it has limitations or bugs or pulls and dependencies you don't really want, debugging that can cost way more time than building a more limited but fully understood solution yourself.
It's a gamble, then, on where your time will ultimately be spent.
It's a calculated risk assessment. An expert doesn't just blindly grab a library. They weigh the potential integration costs, the debugging costs, against the cost of building in-house. It's about understanding where your team's unique skills are best applied. Can you debug that external thing effectively, or are you better off controlling your own destiny, even if it means building something simpler yourself?
So pulling back from all these ambiguities and edge cases, what's the main takeaway?
I think the overarching theme from all that community discussion is there are no hard and fast rules, no silver bullets.
The value of simplicity is totally context dependent.
Exactly. It really boils down to making, as one source put it, a realistic assessment of where time will go over the entire project lifecycle. You're balancing that initial speed against long-term stability, maintainability, and the cost of potential future changes.
Experience plays a huge role here.
Absolutely crucial. A junior developer might hear DTSTTCPW and think it means just hack something together quickly.
Yeah.
Whereas a senior developer understands it means selecting the simplest, proven architectural pattern that meets the known requirements right now. That takes deep knowledge and judgment. It's about informed simplicity, not naive simplicity.
Okay, this naturally leads us to how can you, the listener, actually apply this wisdom? How do you make these judgment calls?
Right. The sources offer a really useful strategic framework. Not rigid rules, but heuristics guiding questions.
Things to ask yourself during design.
Exactly. These help you navigate the choices more thoughtfully. First, requirement analysis. Is this feature, this abstraction, truly required right now for a concrete business need?
That's pure YAGNI, forcing justification based on current value.
Precisely. Second, complexity versus scale. What are the known non-functional requirements? Latency, throughput, concurrency targets. Does the absolute simplest thing you can think of have any realistic chance of meeting those?
Addressing that scalability point we talked about. Sometimes simple is complex.
Third, the cost of being wrong. Estimate the cost. What's cheaper in the long run? Building simple now and maybe refactoring later, or building the complex future-proof thing up front, try to frame it economically.
Weighing immediate cost against potential rework cost.
Yeah. 4, essential versus accidental complexity. Is the complexity you're considering adding essential to meet current needs? Or is it accidental complexity added just in case for some speculative future?
That feels like a core distinction.
It really is.
Yeah.
And 5th, maintainability. This is the ultimate KISS test. Could a new engineer join your team 6 months from now, look at this code, and understand it and modify it confidently?
Thinking about the next person, not just yourself right now.
Exactly. It shifts the focus to the long-term health of the team and the code base.
Beyond those individual decisions, the sources also touched on architectural strategies for building systems that are evolvable, not just simple today.
Right. Things like modularity and encapsulation, build with clear boundaries, stable interfaces, contain the complexity within modules.
Keep things tidy.
Designing for replaceability. Sometimes it's better to build small, focused things that are easy to throw away and replace later if needed, rather than trying to build one giant generic thing that does everything. Agility over premature generalization.
Interesting. Like disposable components.
In a way. Also, the strangler fig pattern, great for dealing with legacy systems. You build new, simpler services around the old one, gradually intercepting calls and replacing functionality piece by piece.
Slowly strangling the old system.
Yeah, hence the name. And finally, prioritizing data structures. As the discussions highlighted, choosing the right fundamental data structures is often the most critical early decision for both simplicity and performance. It's not premature optimization, it's foundational design.
Getting that right can simplify everything else.
Often, yes. It might be the first simplest thing that makes the biggest difference.
Okay, strategies, questions.
Yeah,
But none of this works in a vacuum, right? Culture matters.
hugely. Technical leadership is absolutely key here. They need to foster an environment where these principles can actually thrive.
How do they do that?
Well, first, incentivize simplicity. Actively reward engineers who delete dead code, simplify complex systems, deliver value efficiently. You have to counteract resume-driven development.
Where people choose complex tech just to learn it or pad their CV.
Exactly. Leaders need to value pragmatic results over flashy tech choices. Second, budget for refactoring. Seriously, DTSTTCPW and YAGNI only work long-term if there's a real commitment to paying down the technical debt that inevitably accrues. Time must be set aside for continuous improvement.
It can't just be an afterthought.
No. Third, promote psychological safety. Engineers need to feel safe enough to say, hey, maybe we don't need this yet, or is there a simpler way, without being seen as lazy or unambitious. Pushing back on speculative requirements needs to be okay.
That's a big one.
It is. And finally, lead by example. Senior engineers, architects, managers, they have to walk the talk. Champion simple, pragmatic solutions. Consistently explain the business value of avoiding unnecessary complexity.
So it really needs buy-in from the top down.
Definitely. Culture enables or disables these practices.
Okay, so wrapping this all up, what really stands out to you from this deep dive?
For me, it's that do the simplest thing that could possibly work is so much more than a simple rule. It's not about being naive.
It's really an expert-level heuristic.
Exactly. Applying it well requires a deep understanding of the actual problem, the essential constraints. It needs discipline to defer work based on economic reality, not just technical curiosity.
And it needs that supportive engineering culture, that safety net of continuous improvement we talked about.
The goal isn't just simplicity for simplicity's sake. It's using simplicity as the best strategy we have for creating software that delivers value, is robust, and crucially can evolve over time.
So it really boils down to developing that sophisticated engineering judgment, being able to look at a situation and correctly interpret what the simplest thing means in that specific context.
Yeah, distinguishing essential complexity, the stuff you have to deal with, from accidental complexity, the stuff you added unnecessarily, weighing the costs of doing something now versus later.
Building for today, but enabling tomorrow.
That sums it up nicely.
So maybe a final thought for everyone listening. As you reflect on your own work, maybe even decisions outside of coding, how can you get better at discerning that essential complexity from the accidental? How can you ensure that the simplest thing you choose today actually sets you up for success and adaptability in the long run?
That's definitely something to chew on. It's a continuous learning process for all of us.